Big O is an important tool computer scientists use to measure the performance of an algorithm. In a nutshell, Big O compares how many instructions and how many pieces of memory an algorithm needs with respect to different input sizes. Admittedly, it's also pretty important because interviewers ask you about it and you need to know it as a computer science major for any algorithm-based class. To find the big O of an algorithm, you go through three simple steps. First, calculate a function f of n that gives the number of instructions the algorithm executes given the input size is n. Take the following pseudocode, for example. And as a quick aside, pseudocode is code that's written in plain English, so it's easier to understand. First, we see the easiest two instructions to count are the first two, meaning so far we have two instructions. Then it gets a little more complicated because we have some for loops. We have these two instructions within for loops that run n times, so that gives us an extra 2n instructions. Lastly, we have a nested for loop, meaning for each time we go through the outer loop, we go through the inner loop one time. This means we execute 2n instructions whenever we hit the inner loop, and we hit the inner loop another n times because of the way the outer loop encapsulates it. This makes for 2n squared times that these inner two instructions are executed. If we sum these up, we get f of n equals 2n squared plus 2n plus 2.
If you're struggling with this, go ahead and pause the video now and take a closer look at the individual pieces of the code and see how they fit together so you get a better understanding of how this first step works.
Our second step is that we only consider our dominating term, or a term that will be the biggest when n is very, very large. In this case, this is our 2n squared, and we can eliminate 2n plus 2. In more complex cases, it is worth noting this order of terms. Lastly, we're not concerned with whatever constant coefficients are left over, so we can scratch out the 2 in 2n squared. This is because as n grows large, n squared helps us indicate how the number of instructions grow, and the 2 term only gives us a small amount of detail that we're not concerned with. We're just trying to keep it simple. And that's it. Now all you do is take your result and write it in this format, O of n squared. As a quick aside, this calculation is done for time complexity, and when we're looking at big O for space, we simply replace the number of instructions with the number of items we're storing. It's also worth noting that other examples of big O can get slightly more complex, especially when you get into divide and conquer and recursive type algorithms. But with a little bit of effort or some intense Googling and checking Stack Overflow, you can probably figure it out. Now this is all great, but why do we use this measurement in the first place when we have other metrics such as runtime that seem to fit into the context of a program a little more easily? The reasoning here is that runtime has dependencies that aren't restricted to the algorithm itself. Runtime improves with better hardware. A supercomputer running the same algorithm as a desktop computer will execute much more quickly, even though they're running the same algorithm. Because we're interested in comparing the algorithms and not the computers, we must compare with the number of instructions as opposed to runtime. It's also handy to understand just how much a good algorithm can improve execution time. An algorithm that executes in O of n time can handle an input size of n equals 1000 in, 1,000 steps. An algorithm that takes O of 2 to the n, and such algorithms aren't uncommon, handles an input size of n equals 1000 in it's a number of instructions that has more than 300 digits. And as input size grows, it only gets worse from there. From this idea, we see why big O is so important. Programs consistently handle huge amounts of data, and doing so as fast as possible is the cornerstone of why we study algorithms and data structures in the first place. The better we do this, the more our algorithms can achieve. So keep big O in your thought process as you solve algorithms for class, projects, or whatever it is you're working on. Thanks for watching the video. This is one of my first, and I plan to make quite a few more. If you enjoyed this one, give it a like and hit the subscribe button to show your support. I'd really appreciate it. If you have suggestions for content you'd like to see, feel free to leave a comment below. Stay safe.